about differential equations and slope fields.
Okay.
First of all, when you have a differential equation, which is any equation that has a y prime or a dy dx or that has differentials in it, that's what a differential equation is.
Right.
If it is something like this, there's an easy technique for solving for y, and that is to separate the variables, put all your x's and dx's on one side, all your y's on the other. So this becomes y dy equals x dx. Now I can integrate both sides, and I get y squared over 2 equals x squared over 2 plus some c. And so I can solve for this differential equation. Y is going to equal to plus or minus x. But, bear with me here for a moment, if I have something like this, now I got problems. I cannot separate the variables. It looks like you could do it because you could put the minus y over there, but not really. In other words, there's a huge difference between this differential equation and this differential equation.
Right.
I cannot separate the variables on that differential equation. I can't get all the x's and dx's on one side and all the y's and dy's on the other. So, when you, and remember when I said differential equations is a full year course?
Yes.
Separating the variables is like the power rule in integration. It's easy when it can be used, but also like integration, differential equations, there are about 10 different techniques for solving them.
Right.
And separating the variables is the easiest one, and really the only one they teach you in high school. They don't teach you really many of the others. Like they don't teach you how to solve that one on the right. When you cannot easily solve a differential equation, what you can do is plot the slope fields. And the slope fields will basically map out what the function looks like graphically.
Okay.
Okay? And then there's Euler's method, or Euler's method rather, that allows you to figure out an approximate graph of the true equation. So it allows you to approximate what y would be given a certain x. I can't do that from this because I can't solve for y. But right, using slope fields, you can. Now, I'm going to show you one thing real quick. Here is my difficulty on slope fields and the problems you sent tonight. I want you to look at this problem. This is straight out of your textbook.
Okay.
How you sketch a slope field. Notice, first of all, here, let me draw on here. We're dealing with a differential equation that we cannot solve. We cannot solve it by separating the variables and integrating both sides. There's a technique for solving this, but we're not to that yet. You're not going to get that in high school. However, what they do try to teach you is how to draw slope fields on differential equations that cannot be solved, and then use Euler's method on slope fields or differential equations that cannot be solved, so that you can approximate y.
Okay.
So let's just start at the beginning. This is actually going to be a harder problem than the one you sent me,
Okay.
but I think it's more illustrative. They want you to sketch a slope field based on that differential equation for those 3 points. Well, if I go to that first point, minus 1, 1, that's this point right there, correct? Over here?
Yes.
Minus 1, 1. Plug in the x value and the y value. Oh, what kind of slope do you get?
Negative slope.
Negative what? Specific.
Negative 2.
Negative 2. That's why that slope, I'm going to make a slope at that point. That's a negative 2 slope. Okay?
So when we draw the slope at the point, you're just approximating the.
Well, let's just keep going. You'll catch on here. And it also, they want the slope at that point, 0, 1. Well, if I plug in 0, 1, what kind of slope do I get at that point?
Negative 1.
That's that slope, negative 1. Let's keep going to their third point. At 1, 1, what is my slope going to be?
0.
Correct. So for this particular differential equation, I could just go through any point I want, not just these 3 points, but let's figure out what that's going to be. Well, when x equals 2 and y equals 1, my slope is 1. Y prime is 1.
Okay.
Okay? So I could go through the whole grid of points and come up with a slope field.
Right.
Based on a differential equation that I can't solve. Now, before we go on to your problem, I can make some progress on your problem. I'm just not sure I can make complete progress on it. I want you to understand some of this stuff, though. I think it's very key. And it's going to help when we go to solve your problem. What they're giving us here are 3 slope fields, A, B, and C.
Right.
They want us to match it with these 3 differential equations. Notice I can't solve this differential equation over here. Hold on. I can solve that differential equation.
Right.
Because that's dy. If I try to solve that, that's dy dx equals x, which means dy equals x dx, which means if I integrate both sides, y equals x squared over 2 plus c. Well,
Right.
What is that? That's a parabola.
So that would be A.
That'd be A. You got it. Notice that if I connect all these slope fields, I get various parabolas, and the only difference between them is that C.
Right.
In other words, C merely moves that parabola up and down, basically parallel parabolas, based on what C is. So I could figure out a slope field here, and let's listen, or let's read what they say about it also. From figure 6.3a, you can see that the slope at any point along the y-axis, here, there. All of those slopes are 0. Well, when x equals 0, y prime equals 0, correct? Based on that?
Correct.
So that tells me that A goes with this one. And I could have done it another way. Since I can solve that differential equation, which I did over there, I know I'm looking at a bunch of parabolas. And the only one of those 3 slope fields that looks like a bunch of parabolas is A. Okay.
Correct.
Now, let's do a harder one. That's easy because I was able to solve the differential equation. But the whole point of slope fields is generally when you can't solve the differential equation. Let's look at B. You can see that the slope at the point 1, 1, right here,
right,
is 0. Well, which graph?
So 1, 1.
Excuse me, 1, minus 1.
Okay. So
there's 1, minus 1. And that's the only graph that has a slope of 0.
Right.
How do we know the slope is 0? Substitute the x value and the y value in there. Y prime is slope, so the slope is 0. So based just on the slope field, I can tell that this one has to be this one.
So
and this is a differential equation I cannot solve.
Okay. If on the AP test, would there be a problem like you have a slope field and then it'd be a multiple choice which equation goes with the slope field?
I don't know. I've got a couple of practice AP tests. And when you get done with new material, the last month of the school year, they're going to do nothing but review for the AP test.
Yeah.
Maybe even the last 2 months. In fact, you may be getting close to that point in time now.
Yeah, our teacher wants to be done before spring break.
Okay. And then everything will be reviewed for the AP test. And
yes.
I've got at least 2 practice AP tests that we can use to do that review, and your teacher will have all kinds of problems also.
Yes.
I'm trying to remember what the slope field problems looked like. They might be something like this. And finally, if we look at figure C, you can see that the slope at any point along the x-axis is 0. In other words, it's 0 all along there. Well, that only matches y prime equal y. Now that happens to be a differential equation I can solve. Why? Because I can separate variables. I can divide both sides by y, and I can multiply both sides by dx. Now when I integrate, I get natural log of y equals x. Now to solve that, I'm going to take both sides, exponentiate it to a base of e. Well, e to the natural log of y is equal to y. So the answer is e to the x plus c. And if we look at that slope field, guess what we're looking at? E to the x plus some c. Now, in this case, when that c is negative, it ends up this actually becomes e to the x plus c like that.
Okay.
And that actually becomes e to the x times e to the c, right? In other words, if you have e to the x plus c and you want to break that in, you know it's e to the x times e to the c, right? You're going to add the exponents when you're multiplying.
Correct.
Now, when you see exponents being added, you can separate into e to the x times e to the c. Well, e to the c is the same as c, so this equation's solution actually becomes this, c e to the x, because I'm going to call that c. E to the c is just another c.
Right, it's just another constant.
Right. So the reason this thing gets negative when c goes negative is because you have a reversal of your exponential function. In other words, if c is a negative 1, then y equals minus e to the x. Well,
right.
If you reflect over the x-axis, you get exponential curves that look like that. With me?
Yeah.
Okay. Now, this one right here, I can solve that. And that is of the form of the first problem that you sent to me tonight. Take a look at it. Find it here. Now, I can't orient this, but it doesn't matter.
I thought.
That's
I was trying to get it so when you zoomed in, it would rotate.
I got to come up with a solution. This is actually becoming problematic for me in my online tutoring. I don't know what I got to do, but I got to find some way to read this JPG file and be able to rotate it and zoom in and out on it. And for some reason, my Windows editor that reads these all of a sudden stopped being able to do that.
Okay.
But here's what we have. We have y prime equals x minus 1. Okay? And again, this is not something I really need a slope field on, because if I want to separate the variables, I get this. Now I can integrate both sides. When I integrate the left, I get that. When I integrate the right, I get this. There's my function, y. It's a parabola. So I know my slope fields is going to look a lot like a parabola, just like that other problem I was just showing you where it was y prime equals x.
Right.
That, when I plotted the slope fields, I got things that looked like they were going to form a parabola if you connected the slopes. Well, this thing is easy enough to draw the slope field on. Okay, here, let's do it. When x is equal to 0, what is the slope?
0.
No, plug it into your equation. Remember, that's the slope. Y prime is slope.
Oh, -1. Sorry, I was plugging into the wrong thing.
Okay. So, there's my graph of that point. When x is equal to 1, what is the slope?
0.
So, there's my slope field there. That's at the point 1. And when x is equal to 2, what is my slope?
1.
Now, there's no y in this equation, which means that no matter what y is equal to, I can carry these points. If y is equal to 1, x is still going to be 0 there. It's still going to be -1 there. and so forth and so on. So if I were to draw a slope field for this particular differential equation, it would just kind of look like this. When I go out to x equal 3, well, then the slope's going to be 2, a little bit steeper. And it's still going to be 2 up there. Because there's no y, each row of slopes is going to look exactly the same as I go up and down on this thing.
Okay.
And I'm going to end up with a bunch of parallel parabolas, pretty much. You know what I'm saying?
Yeah.
And the reason is because of that c. In other words, what we're looking at is the graph of that, with c being any number you want. If c is 0, then we probably get this slope field. If c is -1, we get this graph. If c is +1, we get this graph.
Right.
Okay, now the second part of the thing says find a solution to the differential equation the slope field above goes through the point 1, 1. Well, when they give me a given point, like 1, 1, that tells me that the solution is this solution right there. It's whichever of those parabolas goes through the point 1, 1.
Right.
Mathematically, the way I'm going to solve that is I'm going to let y equal 1. I'm going to leave x equals 1. And that gives me this. And if I solve this, I get a c equal to 2 or 1.5. So now I have a particular solution for this differential equation. And it's y equals x squared over 2 minus x plus 1.5. So when you solve a differential equation, you always have a c. Sometimes it's an adder, like it is here. Sometimes it's a multiplier if you started out with a natural log function or something. In other words, we went through that third one, and our answer was y equals ce to the x. So c is a multiplier, so it makes a big difference whether c is positive or negative. And that's why on the bottom side of the x-axis, it changed shape.
Right.
Those exponential curves change shape. Well, in this case, c is an adder. So it doesn't matter what c you have. It's not going to change the shape of my parabola. It's a vertical shift. It's going to be exactly the same shape, only moved up and down varying amounts. So when they ask for a particular solution, I'm not sure if they want you to solve the differential equation like I did, and then algebraically determine what c is, which is what I did, or whether they want you to look at the slope field that you created, and the slope field that goes through this point right here is that slope field, and then figure out the equation of that.
I think it would be find c algebraically.
I think so too, because for one thing, I'm not quite sure how to do that, how to come up with that equation.
Yeah, I don't think you would know. I think the ordering on this question may be weird.
Yeah. And now for the heart. Let's see, number 4 says find the particular solution. Here, I need to erase some stuff so I can read it. Oh, I see what it is. Sketch the solution. On part B, it wanted us to sketch the solution that goes through that point. And we just did that. That is a sketch of that going through this point 1, comma 1. And then find the particular solution, which is what we did algebraically. And this over here is the particular solution for that, meaning
Right.
y equals something with no c's involved.
Okay.
Okay? Now, part D, use Euler's method to using h of 0.1 to estimate little f of, does that say 0, comma 0.5 or 0.5? I can't really tell.
H equals 0.1 to estimate f of 0.5.
F of 0.5. Okay. It's beginning to make sense, a little bit more sense to me now. I'm still not sure I know how to answer this. Oddly enough, I can answer a harder one. In other words, if I make this y prime equals x minus y, now we have a differential equation that we cannot solve. I have no idea what that's going to look like. And
Right.
for a given x, let's say you wanted to estimate what y is going to be when x is 2. Well, this doesn't do much good, right?
Mm-hmm.
I can plug in x of 2, but I don't know what y prime or y is. So I can't really solve for y because I don't know y prime.
Right.
So, Euler's method. I can show you how to do Euler's method for this one. Hold on, maybe I can't. Well, I know I can. No, I got the wrong picture. Didn't. We're going to run out of time here before. Are you kidding me? I sent both 2 pictures. They were both the same. I didn't get the page I wanted to get to demonstrate Euler's method. Euler's method is hard. It might be the hardest thing in Calc AB. I don't know that it's harder than some of your infinite series stuff in Calc.
It's definitely easier than Taylor polynomial series.
It's easier, yeah. No, I know. Taylor polynomials are tough, but I don't know. Once you get them, they're not that tough. But there certainly are some of those tests for concurrence or converging or diverging is what I'm trying to say, are tough, really tough.
Yes.
But Euler's method is pretty tough too. Although, as long as you're dealing with a function of x and y, it's not so tough. If you're dealing with the problem for me on your problem was it's a function of x only, and I'm not 100% sure how to handle that. If you have a function of x and y, I can tell you exactly how to use Euler's method to do it.
Right.
Merely because the book has an excellent example of doing it. Do you have your textbook?
Not with me.
But you have one?
I usually use one that the teacher has or an online version.
Okay. There's an example in the Calculus of a Single Variable by Larson, Hostetler, and Edwards that shows you exactly how to apply Euler's method to a function of x and y, which has got to be harder than just a function of x. It's just I cannot find any in the book that are just functions of x. And the reason is that if it's a function of x, you don't need Euler's method.
Yeah.
Because you can solve that differential equation and find out exactly what y is. Euler's method is to approximate y given the differential equation.
You're right. Yep.
And it's not easy, and it's not something I can even cover in a few minutes. So maybe we need to save this for another session.
Yeah, I think we need tomorrow. We can start with this problem tomorrow night.
Okay, that still doesn't help me a lot. I'm still not sure I know how to solve it when it's a function of x alone.
I could also ask my teacher if
I tell you what, I can help you understand this when you have a harder problem, which is a function of x and y.
Okay.
Maybe you can take that understanding and figure out how to apply it to when it's a function of x alone, like this problem was. You had y prime equals x minus 1.
Right.
That's just a function of x. So
yeah,
that's far easier, should be easier, to apply Euler's method. I think I can probably figure it out by then, by our next session. But I can definitely help you understand how it works when you have a function of x and y. I can definitely do that.
Okay.
And I think that's going to lead us to how to solve it when we have just a function of x. But you might ask maybe, I don't know. I'm not quite sure where to go from here.
Right.
I guess if we had another half hour, I would probably start on teaching it to you as a function of x and y. And then hopefully you could take that and translate it to the easier problem where it's just a function of x. But anyway, let's go with that plan. And if the teacher can give you any assistance on how to do it when it's not a function of x and y, go for it. Try to find out how to do that one.
Okay.
Maybe you can teach it to me.
Okay. Yeah. I'll first ask him if it'll ever show up on the AP test like just a function of x, because I don't think these are AP problems.
I don't think these are either, to be honest with you. There are some problems on the AP test that are going to have slope fields. So you need to understand the concept of slope fields. But I don't think you're going to have to use Euler's method. I don't.
Okay.
On the AP test, but you might check with your teacher. There might be a bonus question or something that uses it. I don't know. It's not something I would really focus on if I was studying for the AP exam. I don't think I would. I haven't looked at that AP test in a while, but all right, I'll let you go.
Okay, thank you for your help today.
And I'll talk to you next time. Do we have something scheduled tomorrow?
Yeah, I think same time, 7:30.
Let me just make sure I've got that in my calendar. Yes, indeed we do. I'll talk to you tomorrow night and we'll pick up on this.
Okay, thank you.
All right, bye-bye.